In this video, we're going to take a look at section 4.2, which is on the addition rule and the multiplication rule. So as I was putting this lesson together, I was surprised to find, because we've updated to a new edition of the textbook, because you're kind of forced to do that every few years. And in this newest edition of the textbook, they took what used to be two different sections and combined them into a single section. And so, and I might skip some things in this lesson because I was treating this material as two different sections, and I am now putting them together into a single lesson. And so it's going to be a little bit lengthy, but just to clarify that 4.2 is on the addition and the multiplication rule. So we're going to look at the addition rule first. We'll get to the multiplication rule here in a little while. All right. Consider the procedure of rolling a single six-sided dice. What is the probability of either rolling an even number or at least a 4? All right, so again, I'm using the phrase at least, which I think I introduced in the previous video, if I recall correctly. And remember, at least means that many or more. So rolling a number that's 4 or higher is what I mean by that. And so this is a situation where we have we're running the procedure once. We are rolling the dice one time. And we want to know, when we roll the dice that one time, what's the chance that I either get an even number or a number at least a 4, at least as big as 4, right? Or 4 or higher. Maybe I should put it that way, right? So rolling an even number or rolling 4 or higher. And so you have to be careful, because, we're giving two different descriptions, but I'm not rolling the dice two different times. This is from a single dice roll. What is the chance that it fits one of these two descriptions, right? Now, we know the probability of rolling an even number. So when you roll a six-sided dice, how many ways could it be an even number? Well, it could be a 2, a 4, or a 6. So the probability, I don't know where I want to write this. The probability of rolling an even number, well, there's 3 ways that can happen, divided by 6 total possibilities. All right, so remember back in the previous video, to calculate the theoretical probability here, we take the number of ways event A can occur, divided by the total number of possible outcomes. There are 3 ways of rolling an even number out of 6 possible outcomes when you roll the dice. What about rolling at least a 4? So this means 4 or higher, so this will be 4, 5, or 6. And so the probability of rolling at least a 4, again, is 3 out of 6. So you might be tempted to think the way you find the probability of rolling either an even number or at least a 4 would be to calculate those probabilities and then add them together. But the problem with doing that, so if I want to find the probability of rolling an even number or at least a 4. So what I've done here is I found those probabilities individually, at least a 4. But what I want is the probability when I roll the dice one time that it's either even or at least a 4. And you might consider adding those two probabilities together. You might think, well, maybe this just equals the probability of rolling an even number, let's try that again, plus the probability of rolling at least a 4, right? Which, if you add those probabilities together, you hopefully realize something doesn't seem right. Right? The probability of rolling an even number is 3 out of 6. The probability of rolling at least a 4 is 3 out of 6. And when I add those two together, I get 1, right? I guess if you want to take a moment to think about that, 3 over 6 plus 3 over 6, you already have a common denominator. So you add the numerators, 3 plus 3 would be 6. The common denominator would stay a 6. And you get 1, which, remember from the previous video, means that it's certain to occur, right? But should one of these two events be certain to happen when I roll a dice? No, because there are certain outcomes that don't fit either description. For example, if I roll a 1, that's not an even number, and that's not at least a 4. And so there are certain outcomes that would not fit either description. So the probability shouldn't be 1. The probability should only equal 1 when one of those two things would be certain to have to happen. And that's not the case with this situation. And so that answer really doesn't make sense. The reason it adds up to 1 is because we are double counting certain outcomes. So notice that we have a 4 here, and we also have a 4 here, right? So rolling a 4 is both an even number and at least a 4, but it's only one outcome, but we're counting it twice. And you can't do that. If it can only occur once when you roll the dice, it can only be counted once. Even though it matches both descriptions, it's still just one possible outcome. And so it gets counted in this 3 and it's getting counted in this 3. So we're counting it 2 different times. So that's why the answer isn't sensible in this case. So what we have to do, so I'm trying to remember I can't remember how I set this up. Okay, so that's the full rule there. What we have to do is remove that double counting that we've done. What else got double counted? Right? 6, right? 6 is at least a 4. 6 is also even. So the event of rolling a 6 is getting counted twice when I add these two probabilities together, but it can only occur once on the 6-sided dice. So we can't count it both times, even though it matches both of those descriptions, right? So we're double counting the 6 as well. So what we need to do is remove that double counting. So if you think about what are all the different outcomes that would match one or the other or both of these descriptions and make a list, 2, 4, 5, and 6, right? Rolling any of these would either match the even number description or the at least a 4 description, and thereby be one of the events that we're monitoring, that we're looking for, right? As long as it matches one or the other, we're counting it as what we're looking for. So any of these dice rolls would be considered a success, right? Part of the thing we're trying to calculate the probability of. 1 and 3 are the only two that are being left out. But if you just take the outcomes that give you an even number and take the outcomes that are at least a 4 and combine those lists together without repeating outcomes, there are 4 different results that would match this description. And then do the probability calculation. There's 4 ways to either get an even number or at least a 4, right? These are the 4 ways you could get one of those two things to happen. So there's 4 ways it can happen divided by 6 possible outcomes. And so you get, which reduces to 2/3, right? So the correct answer is 4 out of 6, or 2/3 if you want to reduce that fraction. However, this scenario, there's not a whole lot of outcomes to consider, but we might be facing some more complicated scenarios with some of these problems. And being able to identify all that double counting might become more challenging. And so what we want to do with this, I don't know, maybe not. Maybe this is the best way to think of it, is like count both of them and then just make sure you remove your double counting. I mean, that is a correct way to approach it. But what is kind of nice about this approach that we're doing down here, yes, we're double counting, but what is nice is that we can just calculate the probabilities of each thing separately, which is usually an easier task than trying to consider them both at the same time. But all we need to do here is subtract out the double counting that we're doing, right? So if I could subtract out the probability that both of these things, sorry, I'm having trouble talking, happen at the same time. So the probability that when I roll the dice, I get an even number that is also at least a 4. So what's the probability that I would get when I roll the dice one time that the number is even and also at least a 4 at the same time? There's 2 ways that happens, right? So this description that I'm giving here are the events where both are happening at the same time, which are the events that I'm double counting. And so since I'm counting them twice in these 2 probability calculations, if I subtract them out once, then the net result is that those outcomes are only getting counted once. So that's the rationale for having this extra term on the end, to remove the double counting that's happening when you're doing the probability for the first 2 events individually, right? And so how many ways can I get an even number that's also at least a 4? There's 2 ways that can happen, either a 4 or a 6. So there's 2 ways for that to happen. I'm running out of room here. Out of 6 possible outcomes. And so we want to subtract that from this total here. And when we do that, we get 3 plus 3, which is 6, minus 2. That's going to give me 4 over the common denominator of 6, right? 4 out of 6, which gets you back to the answer that we got thinking of it this way. And so that gives us this formula. I'm sorry I kind of butchered that explanation. I'm not really happy with it, but I got a ton of videos to record and I'm running out of time, so I'm just going to have to go with it. So this is called the addition rule, obviously because we're adding probabilities together. But if you want to find the probability that either A or B happens when you run a procedure a single time. So again, it's important to recognize that, because the reason I'm emphasizing that is because when we get to the multiplication rule, we're going to be talking about sequences of events. So we're going to be looking at events happening in sequence one after another. So there we're going to be doing multiple procedures. But for the addition rule, it's one procedure. The probability of either A or B happening when you do that procedure that one time is equal to the probability that A happens on its own by itself, plus the probability that B would happen by itself, minus the probability that A and B could occur at the same time. And that removes the double counting that's occurring, right? And so this is the addition rule. Okay. Events A and B are disjoint or mutually exclusive. I should be underlining these words because I'm defining this. I actually like the phrase mutually exclusive. That's the way I remember learning it. But I really hate having to write that out. So I very often will just use disjoint. It's so much easier to write. A lot of people abbreviate this as ME, just to, at least the teacher I had when I took statistics took that measure because she didn't like writing it out either. So mutually exclusive, ME. That means they cannot occur at the same time. So 2 events are mutually exclusive if they couldn't possibly happen at the same time. So, for example, rolling an even number and rolling an odd number. Those 2 events could not happen at the same time. When you roll the dice, it will either be even or odd. It can't be both simultaneously. That means they are disjoint. They are mutually exclusive. And in the case where 2 events are disjoint, and this is kind of what disjoint is referring to, is the Venn diagram representation of such an event. The event of A happening, and I don't know if I'd call this probability of A. I guess I shouldn't argue with the textbook graphics or whatever, but this circle, the fuchsia circle, I don't know if that's the right color, but this, pinkish purple circle is all the ways that A could happen. And this yellow circle is all the ways that B can happen. And they do not overlap, meaning that there's no way that A and B can both happen at the same time. They are completely distinct and separate events. Whereas when they are not disjoint, that means it's possible that the 2 events can happen simultaneously. And that means there's some overlap between those 2 events. So there's, in this area here, these are events where A and B are occurring at the same time. These are outcomes where both happen simultaneously. So if we go back to the dice example, and we think of A as rolling an even number, 2 would be over here. Let me use a different color so it stands out. 5, and we think of B as being at least a 4. 5 would be over here, but 4 and 6 would have to be in the middle because these belong to both groups, right? 4 is an even number, so it belongs to the pink circle, but 4 is also at least a 4, so it belongs to the yellow circle. And same thing with the 6, right? 6 belongs in the pink circle because it's even. It also belongs in the yellow circle because it's at least a 4. And so we'd have these 2 in the shared space, right? Whereas if we think of A as rolling an even number and B as rolling an odd number, they don't share any outcomes in common, right? Even numbers would be 2, 4, and 6. The odd numbers would be 1, 3, and 5. And there's no need for those circles to overlap because nothing would go in that overlap because there's no outcome that belongs in both circles at the same time. And that makes them disjoint from each other. All right. Now, what I wanted to say, and I don't have it typed out anywhere on the screen, is that if A and B are disjoint, then the probability that A and B happen at the same time is equal to 0, right? Because they cannot occur at the same time. It's impossible. And if it's impossible, the probability of that happening would have to be 0. So the probability that A and B both occur at the same time equals 0 if those two events are disjoint. And so if you go back to this formula, when A and B are disjoint, right, then this formula becomes the probability of A, let me redo that because it did a weird thing at the end there, or B would just equal the probability of A plus the probability of B. Because this part would be 0 in the case where they're disjoint. All right. So only when they're disjoint, the formula simplifies to just what we tried to do with that. The first thing we tried to do with the dice rolling example, right? We tried just finding the probabilities of each event separately and adding them together. And if they were disjoint, that actually works. But if they can happen at the same time, then we're double counting things and we have to subtract out the part that we're double counting. All right. Okay, so only if they're disjoint, the formula can simplify to this. If they are not disjoint, you have to use the full thing. So not disjoint, we have to use what was on the screen originally. All right, so maybe I should mark this. I'm just worried about if somebody were just looking at the notes. I said that funny because okay, I'm running out of room there. Maybe if I do that, okay. If somebody's looking at the notes, I was saying notes and writing disjoint, and so I said noints, which was a weird word to say, but only if disjoint, right? Then this part would be 0. Okay, just in case somebody looks at that later. All right, something we talked about in the previous video that we are going to revisit is complementary events, and I might be spelling this wrong. It was underlined in red when I was like typing it out, and now that I think about it, I think that's supposed to be an E there, so I apologize if that's a typo. Remember, complementary events are all like the complement of A is all the ways that A does not occur. So for example, the complement of rolling an even number would be rolling an odd number. It's everything that does not include, all the ways that A would not happen is the complement of A. And we denote the complement of A with a bar over the top of it. So this is the complement of A. The probability that A does not occur, and so what we will often say with this, what I will say is the probability of not A equals 1 minus the probability that A does occur. You can use your algebra skills from college algebra to rearrange this formula, add the probability of A back to the left-hand side, and you get, it's the same formula, but just written in a different way. The probability that A occurs plus the probability that A does not occur has to add up to 1, has to equal 1. Because either A happens or it doesn't happen. So one of these two things has to be true, right? Either A is going to occur or A is not going to occur. And so together, those two probabilities have to account for every possible outcome. And that's why when you add those two probabilities together, they have to add up to 1, right? Because one of those two things is certain to occur. Either A happens or it doesn't happen, right? And so that's another way of putting that formula. So just keep that in mind. We might see that in some of our examples. Determine whether the events are disjoint for a single trial. So again, we're running the procedure once, and we want to know if these two things could happen at the same time. If they can, so it's a little bit of a weird definition, right? If they can happen at the same time, they are not disjoint. If they cannot happen at the same time, they are disjoint, right? So randomly selecting fruit flies with red eyes, randomly selecting fruit flies with dark brown eyes. Could those happen at the same time? No, right? Either the fruit flies are going to have red eyes or they will have dark brown eyes. They can't have both properties, right? So this cannot happen at the same time. So these are disjoint because they cannot happen at the same time. Randomly selecting a college graduate and randomly selecting someone who is homeless. So again, and going back to part A, I'm choosing one fruit fly and I'm measuring their eye color. And I want to know, can they have red eyes and brown eyes at the same time? Can the one fruit fly have both red eyes and brown eyes simultaneously? The answer is no. So therefore, these two events are disjoint. For this, we are going to randomly select a person. And we want to know, if I pick that one person, can they be both of these things at the same time? Can they be both a college graduate and at the same time someone who is homeless? And the answer, unfortunately, is yes, that can be the case. So one person can be both of these things at the same time. And so this is not disjoint. This is not mutually exclusive, not disjoint, because these two things can happen at the same time. All right. So hopefully that makes sense. Moving on, find the complement. So here I actually have the correct spelling, so I apologize that I misspelled it earlier. Women have a 0.25%. That's not 25%. It's 0.25% rate of red-green color blindness. If a woman is randomly selected, what is the probability that she does not have red-green color blindness, right? So this is, the case of using the formula for a complement, and probably the easier, remember we talked about two different ways of structuring that formula, but we want to use the first one for this. The probability that a woman does not have red-green, I'm going to abbreviate color blindness if that's okay, color blindness, according to the formula for the complement, is 1 minus the probability that they do have red-green color blindness. So have red-green, let's see if it'll fit, color blindness. Okay. So again, if we think of this as being event A, having red-green color blindness, the probability of not A equals 1 minus the probability of A. And I'm not sure why I didn't put that all the way through here. It should be all covering the whole thing. All right. And so this is using that formula where A is having red-green color blindness. We want to know the probability of not having A, and we can calculate that by taking 1 minus the probability that A has occurred, that they do have red-green color blindness. All right, so this is going to be 1 minus, and that's the probability we're given up here. Right? This is the probability that A occurs. So we're being told, here's the probability that a woman has, I'm saying the number for some reason, here's the probability that a woman has red-green color blindness. It's 0.25%. We want to calculate the probability that they do not have red-green color blindness. And so we'll take 1 minus the probability that they do. And it's going to be, it's going to be tricky because this was a percent. To calculate this probability, like this 1 is 100%, but we want to just keep it as a 1. So what we need to do is convert this percent to a decimal number. Now you might say it's already a decimal, but it's in percent form. We want to change it back to standard form, or I think of it changing it to a decimal form. Even though it already has a decimal in it, it's in percent form right now. We need to change it to numerical form, however you want to describe it, which means we take the decimal and move it back to the left twice. And so we're going to get 0.0025. That's 0.25% right there. 1 minus that is going to be 0.9975. And that'd be the probability, if you randomly select a woman, that she does not have red-green color blindness. 99.75% chance that the person would not have red-green color blindness. All right. Sorry, this table is kind of fuzzy again. This is the table we saw in the previous video for section 4.1, and it's about polygraph test. And we have a scenario where I don't know how the information was determined, but we have people taking a polygraph test, and we know the result from the test, whether it was positive or negative, positive that they lied or negative that they did not lie. And we also know whether they actually lied or not. I don't know how we know that. Like I said, maybe this was some kind of quality assurance testing of the polygraph machine, and they instructed people whether to lie or not, and then they check to see what result they got. And so we know whether the person actually lied or not. And that's given by these columns here. So everybody in this column actually lied during the polygraph test, whether the machine said they did or not. Right? So these 42 people lied, and the machine caught them in that lie. They got a positive result that they were lying. And so for these 42 people, the machine worked the way it should. They told a lie, and the machine caught them lying. But for these 9 people, they told a lie, but the machine didn't catch it. So they told a lie, but the machine said they weren't lying. So these 9 people, the machine didn't work the way it was supposed to. So all the people in this column lied. All the people in this column did not lie. They told the truth. In the rows, we have what the machine's results were. So everybody in this row, the machine indicated they were lying. Whether they actually were or not, that's a different question. But the machine said they were lying. In this row, the machine said they were telling the truth. Right? So that's how that table breaks down. Assume that one subject is selected at random from this study. Right? And we're going to answer some questions. What is the probability that the selected subject had a negative test result? So this is really reviewing what we talked about in section 4.1. There's no or here. This is not the addition rule that we have to do with this. So what was it again? Negative? What was the probability that the subject had a negative test result? So we need to find all the people. So how many ways could we select somebody with a negative test result? That number is the number of people that got a negative test result when they took the polygraph test. So I just need to find out how many people got a negative test result from the polygraph test. That's the number of ways I could choose somebody that had a negative test result. And so negative test result would be this row here. Again, not whether they actually told the truth. That's not what the probability is asking. It's not asking the probability that somebody was telling the truth. We're just asking what's the probability that the machine said they were telling the truth, whether that's the case or not. And that's this row here. Everybody in this row got a negative test result. And so we want to add these up. So if I add these together, 32 plus 9 is going to be 41. So 41 people received negative test results out of 98. I don't know if you remember that from the last one. And I don't know, I thought it was on one of these questions, but I guess I left it out. But there was 98 people in this study altogether. So N is 98. So there's 98 people we could choose from. 41 of them had a negative test result. So the probability is going to be 41 over 98. So that's the answer for part A. For part B, what is the probability that the selected subject did not have a false negative result? So there's a lot of descriptions in here you don't want to overlook, and I'm already kind of out of room. So let me scroll down here. So for part B, we want to find the probability that the person did not have a false negative. There's a lot of negative terms in this question, isn't there? So the probability that somebody did not have a false negative result. Whenever you see the word not in a probability question, you should immediately think of the rule for complements. The probability of not having this characteristic, which we can label A if we want to. The probability of not A is equal to 1 minus the probability that A did occur. Right. Whoops, I hit the wrong button. Oh, geez, now I have to erase this instead of undoing it. Okay. Let's try that again. And again, A in this case is getting a false negative result. All right. So the probability of not having a false negative result is 1 minus the probability of having a false negative result. And that's going to be an easier probability to calculate. So all I need to do is find out how many people had a false negative result, divide that by 98, and that gives me that probability. And then I'll take 1 minus that probability to get the probability of not having a false negative result. All right, so going back to the table, false negative is labeled here for us, right? Here's false negative. There were 9 people who had a false negative result, right? It's very specific, not just negative, right? There's 41 people that got negative test results. We specifically want the people that got a false negative, meaning the lie detector said they were telling the truth when in fact they were lying. It was negative, falsely negative, right? It was negative when it shouldn't have been negative. 9 people had that experience, right? 9 out of 98. And so that would be the probability of a person having a false negative result. So to find the probability of somebody not having a false negative result, we take 1 minus that probability that we just found. Right, and so we talked about this, I think, in the last video as well. When you're subtracting these, and you'll do these enough. Either you're doing them on your calculator and you're fine that way, but if you're doing them by hand, with enough practice, these are not that hard to do. You get the hang of them pretty quickly. So you think of this as 1 over 1, get a common denominator, which is just going to be the 98. And so we'll get 98 over 98, right? 1 always becomes the same number on top and the same number on the bottom. Whatever that common denominator needs to be, it'll just be on the top and the bottom for when you convert 1 to a fraction. Minus 9 over 98. So it's just going to be 98 minus 9, which is going to be 89 over 98. So that's kind of weird, isn't it? So, but that would be the probability of not having a false negative result. So choosing someone from the study and that person not having a false negative result, the probability is 89 over 98. All right, so let's see if I can fit the last problem on the screen here in this space. Let me scroll back up so we can read it. What is the probability that the selected subject did not lie and had a negative test result? Okay, did not lie and had a negative test result. Now we're going to talk about and as a probability thing later, but when we talk about and later in this video, it means in sequence that you're going to actually pick 2 people. And what's the probability the first one fits this description and then the second one fits this description, which is not the case for part C. So you got to be careful when you see the word and, whether you should use the multiplication rule, which we're going to look at later, depends on whether you're picking one person or you're picking multiple people in a sequence. If it's multiple people in a sequence, then you use the multiplication rule, but that's not the case for part C. We're selecting one individual, and we want to know the probability that that one person did not lie and also had a negative test result. And are these mutually exclusive, right? No, they're not. It is possible for both to be true at the same time. That one person could have told the truth and also got a negative test result. So we want people who did not lie. So let's look at the table. This column are the people that did not lie, right? So that's what we're being asked for here, right? Did not lie. So anybody in that column fits that description. And then we also want that the person we choose to have a negative test result, which is this row. So anybody in this row fits that second description of having a negative test result. Anybody in the first column fits the description of not lying. And we want to know the probability of choosing somebody that fits both descriptions, which are going to be these 32 people here. So there's 32 people in the study that did not lie and also got a negative test result, which is what they should have gotten, right? They didn't lie, and the lie detector test determined that they didn't lie. So for these 32 people, the test worked the way it should. So there's 32 people altogether that fit that description. So even though it's a more complicated question, it's the same probability calculation that we've done in many problems so far. It's how many ways can it happen divided by the total number that you could choose from, or the total number of possibilities, right? So the probability that picking one person and they did not lie and had a negative test result. There's 32 ways we could choose somebody that fits that description. Right? There's 32 people where both of those things happen to them out of 98 people that we could choose from altogether. And so that would be the probability there. So it was a little bit harder to filter out, to count down to those people that fit that description. But once you have that number, it's the same probability calculation we've done on multiple problems, which is how many ways can it happen divided by the total number of possibilities. Right? So that's part C. Now part D, what is the probability that the selected subject lied or had a positive test result? Now when you see the word or, that's the addition rule. That's the rule that we started off this section talking about. So I want to know, and I'll do the problem up here. The probability that the subject lied or had a positive test result. Let's try that again. And so because of the or, that's the addition rule. And we will calculate that by taking the probability that the person lied, so we can find that probability first, plus the probability that a person has a positive test result. But then we might be double counting, right? Because it is possible for a person to fit both descriptions, that they lied and also got a positive test result. And those people are getting counted in both probabilities. They're getting counted with the liars, and they're getting counted with the people that got positive test results. And we don't want to count those people twice, right? They only occur once in our group of people. Each person should only get counted once. So anybody who lied and got a positive test result is getting counted twice here. To make sure they get counted once, we have to subtract out those people one time, right? We're counting them twice, we subtract them out once, so the net result is that each person gets counted one time, right? Who's getting counted twice? The people that both lied and, sorry, I'm kind of squeezing those a little too close together. So this is lied here and got a positive test result. Those people are getting counted twice, so we will subtract them out once so that the net result is they're getting counted once. Right, and so what's nice about this is that we can just kind of focus on one probability at a time. So what's the probability that if I choose somebody at random that they lied on the lie detector test? Well, that would be everybody in this column here, right? These are the people that lied. Everybody in this column, so I want to add them up. And so we have 42 plus 9, that's going to give me 51. So 51 people lied during this study out of 98. So the probability if I pick a person at random that they lied is going to be 51 out of 98. Plus, what's the probability if I pick a person at random that they had a positive result from the lie detector test? That's everybody in this first row. Right? Everybody here got a positive result from the test, whether they lied or not. We're not making that distinction, right? We're just saying, what's the probability that you pick somebody that got a positive result, whether they told the truth or they lied? And it's going to be everybody in this row here, which is going to be, you have to add these together, 15, let's try that again, 15 plus 42, which is going to be 57. So 57 people got a positive test result. 57 out of 98. And so the probability would be 57 out of 98. Now, if you weren't careful about the double counting and you just added these probabilities together, you would get a number that was over 1, which is not possible. Probabilities cannot exceed 1, no matter how complicated the question is. When you add up the probabilities, they cannot add up to more than 1. If that happens, it means you're double counting because the final answer needs to be something between 0 and 1. So this would add up to 108 over 98. That's bigger than 1. That's a nonsense answer. The reason that happens is because we are counting a certain group of people twice, and we can actually see that by where our circles are drawn, right? So here are the people that lied. Here are the people that got positive results. These 42 people are getting counted in both groups. They're getting counted with the liars. They're getting counted with the positive test results. And so we're counting these 42 people in both groups, and we can't be doing that, right? These people can only count once, just like everybody else is counting once. And so these are the people that both lied and got a positive test result. So what's the probability of picking somebody who fits both descriptions? 42 out of 98. And so that's this probability. These people are the ones that got counted twice. There's 42 of them out of the 98. That's the probability that you would pick a person that fits both descriptions at the same time, which are the people that are getting counted in both groups. We have to subtract them out once so that everybody's getting counted the same number of times. And that's going to give us the correct answer, right? Which is going to be 108 minus 42. It's going to be 108 minus 4, 66. I hope I'm doing that right. 66 over 98. All right. And so that's the answer for part D. Okay, so that's how that works. Okay, what is the probability that the selected subject did not lie or had a negative test result? So again, same situation. The probability that the person did not lie, or, so when you see the word or, you should think that's the addition rule, had a negative test result. Now first, what I always check for is, are these mutually exclusive? Are they disjoint? Because if they are, the formula becomes simpler, because the probability that they happen at the same time would be 0. But these are not disjoint. These can happen at the same time. There are people in the study who did not lie and also got a negative test result. So there are people that can have both characteristics. So that it's not disjoint. So we have to worry about that double counting, and we have to subtract out that probability. So why don't you pause the video to do this problem? So write this down, right? This is for part E. The probability that a person did not lie or had a negative test result. That's the probability you want to find. And then I'll go back to this screen so you can pause it on this to get the numbers that you need. And I'm sorry, I've really marked up on this. Maybe I should just erase all of this just to make it easier for you to work with. All right, so pause the video, get the numbers you need off of this chart, and calculate that probability, and then resume the video to see if you came up with the right answer. Okay, so the answer you should have come up with on this problem is 56 over 98. So there's the work that went into getting that answer. The probability of choosing somebody who did not lie is 47 out of 98. There was 47 people who did not lie. You have to add up that column to get that number. The probability of choosing somebody that got a negative test result is 41 out of 98. You have to add up that row to get that number 41. And then the people that are being double counted, there's 32 people that fit both descriptions. There's 32 people who did not lie and also got a negative test result. So 32 people are the same 32 people are being counted in the 47 and in the 41. We don't want to count them both times, so we have to subtract them out once so that the net effect is that they are only being counted once. So 32 over 98, that's the probability of choosing somebody who did not lie and also got a negative test result at the same time. And when you add and subtract, you get 56 out of 98. And so I'll just go back real quick to the table so you can kind of see how I got the numbers. 47 from adding up this column, 41 from adding up this row. And again, if you circle the numbers, the row and the column you're adding up, you'll see the overlap. You'll see the people that are getting counted twice, right? These 32 people are being counted in both groups. That's why we have to subtract them out once. Okay. Part F. What is the probability that the selected subject had a positive test result given that the subject lied? So this is maybe it's a little out of place since we haven't really talked about that concept yet, but this is called conditional probability. And in fact, section 4.3, which I thought was going to be on the multiplication rule, but is actually going to be in this section, is on that topic of conditional probabilities and probabilities of at least one, which you might see a little bit of in this video as well. And so I'll maybe get more into this in the next video. I really haven't decided if I want to cover that material, honestly, because I'm going to mention it here. But the given part here is you're starting with the assumption, basically you're narrowing down your population to those people that fit this description. So given that we have somebody that we know lied on the test, so we're narrowing down our pool to only to the people that lied. I kind of said that funny, but we've narrowed down our pool that we're selecting from to only to the people that have lied. And we've let everybody else go home. So think of it as like we're conducting this study and we have 98 people, and now we've let all the people that told the truth go home. And right now we only have the people that lied still in the building. And given that we have narrowed it down to only the people that have lied, what's the probability that from that group only, I would pick somebody that got a positive test result? All right, so we want the probability that somebody got a positive result, given that they lied on the polygraph test. All right, so going back to this chart, assuming that we've let these 47 people go. They are no longer in the building. We sent them home. So we are only considering the people that lied on the test, right? These are the people that lied. There's 51 people here that have lied, right? Out of that 51 people, what's the probability that I'm only selecting from those 51 that they got a positive test result? Well, here, this is the row for positive, but these people aren't here anymore. We sent them home. How many people are left that have a positive test result? Just these 42. Out of how many people are currently in the building right now? 51, right? So the probability is if you narrow it down to just the people that lied, there's only 51 people to choose from. So now that's your denominator. That's the total number of people available. And out of those 51, only 42 of those people got a positive test result. So it's still the same probability calculation, but you've just narrowed your population down based on this characteristic. And based on that characteristic, then you want to find the probability of a certain thing happening, right? So it's going to be, I already forgot the numbers. I went too far. 42 out of 51. I went the wrong direction there. Okay. 42 out of 51. Sorry if that was disorienting. I'm not really thinking about what I'm doing, evidently. So 42 out of 51 would be the correct answer for that. All right. So that would have been the end of traditionally what 4.2 covered. And that would have been a great video because it would have been less than 50 minutes, which would be a record for me, especially it's been a while since I've done a video that quickly, but they added 4.3 to section 4.2. So this would have been the start of my 4.3 material, but I had to edit it to say this is still 4.2 and we're just continuing in that section with the multiplication rule. All right, so we're still doing 4.2, and this is going to be another probably 45 minutes. I apologize. So it's going to be kind of a long video. Assume that you have two 6-sided dice, one red and one blue. And I think we talked about this back in section 4.1. What is the probability of rolling a 4 with the red dice and then a 3 with the blue dice? So you can sort of think of just rolling these dice at the same time, but I'm trying to word it in such a way that we're rolling one dice at a time. We will roll the red dice first and the blue dice second. What's the chance that you get a 4 with the red dice and then you get a 3 with the blue dice? Which is not the same question as asking what are the chances that you roll a 7. I'm being very, very specific about the exact sequence of the dice rolls and how they have to turn out. So it's not just any 7, it's specifically a 7 that you get with a 4 on the red dice and a 3 on the blue dice. All right. So I'm gonna pause for a moment and pull up the chart from our notes in section 4.1 with rolling 2 dice, one red and one blue, and so then we can kind of figure out the probability from that. So just give me 1 second. Okay. So on the screen, these were my notes from the video for section 4.1. And this was the same scenario of rolling. Now here we were talking about rolling 2 dice at the same time, but the dice were colored differently. One was red, one was blue. And so it really is kind of the same scenario as rolling 1 dice at a time. It kind of the math works out the same either way, and the description of the possible outcomes is the same either way. And this is what we had here. And we found out in section 4.1 that when you are rolling 2 dice, whether together or one at a time, there are 36 possible outcomes if they're 6-sided dice, right? There are 36 possible outcomes from rolling 2 6-sided dice. So what we're looking for here is specifically the outcome of rolling a 4 with the red dice and a 3 with the blue dice, which is going to be this outcome right here. And that's it, right? There's only one way to get that particular sequence, and that's this outcome right here. 4 with the red dice, 3 with the blue dice. This is the only one that fits that description out of all 36 of these, right? And so the probability is going to be 1 over 36. There's only one way for that particular sequence of events to happen out of 36 possible outcomes that could have happened, right? So that's one way you could approach this, is what's the probability of, let me use a different color here. What's the probability of rolling a 4 with the red dice. And then, with the word here, a lot of times they'll just put and, but I like to put and then to just drive home the point that we're talking about two events in a row. One thing happening first and then another thing happening second. Rolling a 4 with the red dice and then a 3 with the blue dice. And we just saw in our chart that that only happens once in our entire chart out of 36 things that could have happened. And so that would be the probability. However, that'd be a lot of work and may not even be possible in some scenarios of trying to map out every possibility of these sequences of events and then finding the ones that fit our description. And even if that is possible, it's a lot of work. Is there a shortcut that we could use here? And the answer is yes. So what we could do, and so with that chart, I don't want to reproduce it here, and I would go back to it. It's still on my screen, but then I can't write on it because it's not in my software that I need to be able to write on it. And so I want to write something down. So we have 1, 2, I'm not going to write them all out. 6 for the red dice, right? And then for the blue dice, we have 1, 2, 6. And I pointed this out in the last video as well, that you have 6 rows and you have 6 columns, and that's how you're getting 36 different possible outcomes with the 2 dice rolls, right? So if you look at the dice rolls separately, there's 6 outcomes when you roll the red dice, and only one of those gives you a 4. And there are 6 outcomes when you roll the blue dice, and only one of them gives you a 3, right? And the 6 times the 6 is how we get the 36 here in the first place. So if I consider the dice rolls individually, the probability of rolling a 4 with the red dice, well, there's only one way to get a 4 out of 6 possibilities when you roll the red dice by itself. And the probability of rolling a 3 with the blue dice, well, there's only one way to get a 3 out of 6 possibilities with the blue dice. And the 6 times the 6 is how we get the 36 here in the first place. That seems to make sense to do with these 2 fractions. That if I multiply these 2 fractions together, that will multiply the 6's together to give me the 36 in this denominator. And so in fact, that is another avenue for calculating this probability, is to calculate the probability of these events happening separately and then multiply those individual probabilities together to get the probability that they would happen in that sequence. And so we get 6 times 6, which gives me 36. So I'm just going to write it again over here. We're multiplying these 2 fractions together. 1 times 1 still gives me 1, which is what I have here. 6 times 6 gives me 36, which is what I have here. And so we get 1 over 36 that way. And so this is the multiplication rule. So if you're looking at the probability of a certain sequence of events happening in that particular order, then you can calculate that probability by calculating the probability of each individual event separately and then multiplying those probabilities together. And again, you can kind of see why that would make sense for, the denominator. It's the total number of things that could happen, which we calculate by taking the number of rows here times the number of columns, right? That tells me the total number of things that can happen. But that also happens if you multiply these probabilities together, right? The denominator, this is all the ways that the first event can happen. This is all the ways that the second event can happen. So how many ways can those happen together? You multiply them together, because this will give you the number of columns. This gives you the number of rows. And that's true for the dice rolls, but that would be true for any kind of events. That if you're looking at 2 things happening in sequence, the number of ways the first thing can happen would determine the number of columns you have. And the number of ways the second thing can happen would determine the number of rows that you would have when you're putting them together in a sequence. That will always happen. And so it makes perfect sense to want to multiply these denominators together to find the total number of different things that can happen with the 2 events that you're considering, right? And so, so that kind of motivates why this, would make sense. All right. So is this the multiplication rule then? If I want to find the probability that A happens first and then B happens second, is that always just going to be the probability of A happening times the probability of B happening? Put a question mark here because not quite. It's not quite that simple. It works for the dice rolls. This actually is perfectly fine for the example we just did. But there's other situations where this won't quite be the correct answer. Right. And so let's see what I have next. So And we'll come back to that. All right, but I need to talk about something else first before we fix that. Events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Dice rolls are independent, right? What I roll with the red dice does not affect the outcome that I get on the blue dice, which means the roll of the red dice does not affect the probabilities of when I roll the blue dice. Those events are independent of each other. One is not going to affect the other. So, if they weren't independent, it would be the case that, well, if I roll a 4 with the red dice, that means I'm more likely to roll a 3 with the blue dice. No, that doesn't change the odds of rolling a 3 with that blue dice. It's a whole separate dice, and it's going to have the outcomes it's going to have independent of whatever you ended up getting on the red dice, right? Now, sometimes we can trick ourselves into thinking that might be dependent. For example, if I flip a coin 5 times and it's heads every single time, when I go to flip the coin the 6th time, a lot of people would think, well, I'm due for tails because I've gotten heads 5 times in a row. I should be getting some tails here eventually. So I'm more likely to get tails now when I flip it the 6th time. And that is not the case. It's still 50-50 when you flip the coin the 6th time, right? You're still 50% chance to get heads. It doesn't have a memory, right? The coin doesn't remember that, oh, I've given heads 5 times already. I need to give tails this time, right? It has no consciousness like that. It can't take that into account. When I go to flip the coin that 6th time, it doesn't have a memory of the outcomes that came before it, right? And so it's going to be 50-50 again. 50% chance heads, 50% chance tails. All right. Same thing with dice rolls, right? If A and B are not independent, they are said to be dependent. And so you can have events that are dependent. I'm trying to think of an example off the top of my head without, the examples I'm thinking of, I have one good example in mind, but I'm saving that. I want to talk about that later in the video. I'm trying to think of a simple example. And okay, here's one. I don't know. This is from the textbook actually. But if you're considering, so it's about, I don't know, let's see if you can figure it out. So you have a computer plugged into the wall, at least I do. Right now, I know a lot of people now, we charge our devices up and they run on a battery, but let's assume that my computer right now that I'm recording on is plugged into the wall. This happened yesterday, actually. We had a bad storm yesterday. And then my computer shut down. I was in the middle of getting this lesson ready. I was kind of at the end of it, actually, not really in the middle. And my computer just shut off on me, which thankfully I was on Google Slides. So, kind of just automatically saves your work as you're working on it. And then, so my computer just powered down. So I lost power to my computer. Now, does that change the odds that I've also lost power to my refrigerator? Yes. So losing power to my computer changes the probability that I will have lost power to my refrigerator because they run on the same power system. They're both plugged into my house, right? So those are dependent events. When one occurs, it changes the probability of the other one occurring. When my computer all of a sudden powers down for no reason, just completely shuts off, that increases the probability that my refrigerator has also done the same thing. It doesn't guarantee it. It could just be I blew a fuse in just this room and it doesn't affect the refrigerator, or it could be my computer just broke or something. But the odds do go up that if my computer just shuts down for no reason, that other things in my house have probably shut down as well, right? The odds go up for that. So that'd be an example of dependent, right? Events where one affects the other one. Okay. If A and B are independent, then yes, this formula is true. The one that we just talked about a moment ago. So this would be the multiplication rule. And this is the rule that we just used to do the problem with the dice rolls. The probability of rolling a 4 with the first dice and a 3 with the second dice was 1/6 and 1/6 because those events are independent of each other. I don't have to make any adjustments or take anything else into consideration. I just find those probabilities individually and multiply them together, and I get 1/36. If they are independent, this works. If they are dependent, we have to modify that second probability, right? Because if the probability of B occurring can be affected by A having occurred, then we have to adjust the probability for B, assuming A has happened. Because when I'm asking you for the probability of A and then B, A is happening first, and then B is happening second. Now, if A doesn't occur on the first trial or procedure or whatever, then it doesn't happen, right? The sequence is ruined, right? But assuming A does happen, like it's supposed, not like it's supposed to, I shouldn't say that, but like if A does occur on the first one, as we're, monitoring, it's the thing we're looking for, right? So if the thing we're looking for does happen for the first event, if A does happen, then we can move on to the second event. And we want to know what's the chance that B will now happen on the second event. But we only get that far if A happened first. So when we go to calculate the probability for B happening, we want to take into account the fact that A must have already occurred for us to have gotten that far. And so this notation here is that conditional probability that we talked about just a few moments ago. This is the probability that B occurs given that A has occurred, right? So take into account that A has happened in calculating that probability for B, which is always a good idea. So if you're not sure which formula to use, you should always use this one. And in the case of the dice roll, you would say, okay, what's the chance that I roll a 3 with the second dice? Assuming, given that, I rolled a 4 with the first dice. Well, rolling a 4 with the first dice doesn't affect if I roll a 3 with the second dice, so I don't have to really consider anything there, right? And so it doesn't hurt to think about, and then maybe you realize, well, that first event actually doesn't impact the second event, and so there's nothing to consider. But other situations will, and like I said, I have an example of that. So this is really the proper multiplication rule. All right. Okay. Oh, I'm sorry. Maybe I should have put these on 2 separate windows so it doesn't look so scary. In sampling with replacement, when a selection is made, it is replaced before the next selection is made. And this might seem like, I just went off in some random direction and I'm ignoring what we were just talking about, but it's actually very related to dependent versus independent, right? So in sampling with replacement, when a selection is made, it is replaced before the next selection is made. So either the thing that you picked the first time is placed back into the pool, into the population, or it's also okay if you replace the thing that was chosen with a new thing, as long as it has the same exact characteristics of what it's replacing, right? So, for example, I guess it's just what's on the top of my mind because I know we're about to talk about it, but like I have my example we're going to talk about is a bag of marbles, right? And so if I have a bag of marbles of different colors and I take a red one out, so I select a marble from the bag, it's a red marble. With replacement means I either put that red marble back into the bag before I pick a second marble, or I replace the red marble with a new red marble, so it's still red. So either way, you're back to the original starting population, either with a new marble of the same color or putting the original marble back, right? You're back to the original population you started with. That's how with replacement works. In sampling without replacement, when a selection is made, it is not replaced before the next selection is made. This means the next selection is made with one less element available in total, right? There's one thing missing now from the population, and also one less element available of whatever characteristics that element possessed, the one that was taken out first, which is going to affect probability. So this is actually going to be, with replacement, keeps those selections independent because you're always going back to the original numbers, and so the probabilities won't change. But without replacement, you now have less things to choose from, you have less things of that particular characteristic, and that's going to affect the probabilities of the next selection that you make. And so we have to make adjustments because of that. So for example, with the marble example, I was trying to think of a different word to use there, but I couldn't think of one. If I take the red marble out and I let you keep it, right? So we pick a marble out of the bag, it's a red marble. I say, here, you can have this red marble. and I don't replace it, I don't take the red marble back, and I don't put a new red marble in, that's without replacement. So now when I go to select another marble from the bag, there's one less marble altogether in the bag, but there's also one less red marble. And so if I'm wanting to know what's the probability that I would pick another red marble, well, there's one less marble and one less red marble, and that's going to affect both the numerator and the denominator when we calculate that. Okay, so that's with replacement, without replacement. You want to be cognizant of that detail in these problems that we're about to do. So whenever they're saying, what's the chance that this happens first and this happens second, you need to determine whether that second selection is being made with replacement or without replacement, right? Because that's going to affect the math that you do. All right, so here's the marble example that I was trying to avoid giving away. Consider a bag containing 10 marbles. We have 10 marbles altogether. There are 3 green marbles, 3 red marbles, 3 blue marbles, and 1 gold marble. And so, again, this used to be section 4.3, and so I would actually use this example to review 4.1 and 4.2, but this is still part of 4.2 now, so I still think these are review questions, but we've kind of done a lot of reviewing already in this video, so I apologize. Maybe this is a little bit too much. But when selecting one marble at random from the bag, what is the probability that it is a blue marble? All right. So the probability that it's blue, it's the number of ways it can happen divided by the total number of possibilities, right? So how many blue marbles are available to be selected? There are 3 blue marbles in the bag out of 10 marbles that I could choose. That's the probability of picking a blue marble. All right. So same example, I just copied it over on every page so we wouldn't have to keep going back and looking at those numbers. When selecting one marble at random from the bag, what is the probability that it is a gold marble? All right, so, and actually I'm asking this question, it's a little redundant, it's kind of like the first one, but I have another example we're going to look at later that is, I think, I don't know, blows my mind, and it only really has that effect if we know this thing first. So that's why I'm having us calculate this. How many ways could I choose a gold marble? There's only 1 in the bag that I could choose out of 10 marbles available. So 1 out of 10 is the probability that if I pick a marble out of the bag, it will be a gold marble. All right. When selecting one marble at random from the bag, what is the probability that it is not a red marble? All right. Well, the probability that it's not red, again, you could add up what are all the different non-red marbles in the bag. It's not that hard to do. It's maybe even easier than thinking of it this way, but I like to use this rule whenever it's applicable. It's the complement, right? Whenever you see the word not, you should think complements, right? So the probability of not red is 1 minus the probability of selecting a red marble, right? And the probability of selecting a red marble is 3 out of 10, right? Because there's 3 red marbles out of 10 altogether. So we take 1 minus that to get the probability of selecting a marble that's not red, right? Which is going to be 7 out of 10. All right. And so that's the probability of getting a marble that is not red. When selecting one marble at random from the bag, what is the probability that it is a green or a red marble? Are these events disjoint? The answer is yes. So if you're picking one marble from the bag, can it be both characteristics at the same time? Can it be both red and green at the same time? Not with these marbles. Now, I know if you're thinking like, well, I've seen marbles before and they're multiple colors. Yes, that's true, but these marbles are solid colored. So either it's green or it's red, it can't be both. So they are disjoint, they are mutually exclusive, which means our formula becomes easier, right? So the probability of having a green or a red marble will be the probability of getting a green marble plus the probability of getting a red marble. And we don't have to do the minus thing because there's no double counting here. Right, so when it's mutually exclusive, that last term, right, well, I'll go ahead and write it, but we'll cross it out right away, would be the probability of getting a green and red marble at the same time. Not in sequence, not a green one first and a red one second, but when I'm choosing one marble that it's both green and red at the same time, can't happen. The probability is 0. Right, and so that term just drops away. We don't have to even consider it. So that's the advantage of being able to determine that 2 events are mutually exclusive. You don't have to consider that last term. You can just focus on What's the probability of getting one? What's the probability of getting the other? And just adding those two probabilities together. And the probability of getting a green marble is 3 out of 10. There's 3 green marbles. The probability of getting a red marble is also 3 out of 10. So what's the probability that when I select a marble, it's either green or red? There's 6 ways for that to happen. 3 that are green, 3 that are red. So 6 ways to either get green or red when I pick a marble out of the bag. 6 out of 10, which you can reduce, but I'm just going to leave it as 6 over 10. All right, and that was supposed to be a review question because that's the addition rule, which used to be in a previous section, but I'm reviewing from earlier in the video, I guess. All right, so now we're up to the multiplication rule questions here. When selecting 2 marbles at random from the bag, so I'm picking 2 marbles now, one at a time, what is the probability that the first marble is green and the second marble is blue? Now, if you're jumping right into, okay, the probability that we get a green marble is 3 out of 10. The probability of getting the blue marble is 3 out of 10, and it's multiplication rule, I'm going to multiply. You are jumping ahead because I withheld a crucial piece of information on purpose to see if you would catch this, because you have to be looking for this detail in order to answer this question correctly, right? Is this being done with or without replacement? So you should, on the homework, it should somehow indicate that. They don't always use that exact phrasing, but something in the details of the problem should indicate to you whether it's being done with or without replacement. One common way of doing that is if they use the word different. If they say you're going to select 2 different marbles. Well, the only way to guarantee that they're different is if you're selecting it without replacement. So they don't use the phrase without replacement, they just say different. But if they have to be different from each other, you can't put the marble back in the bag because you might pick the same one again. So you have to keep the marble out of the bag, which means it's without replacement. So you want to look for clues like that to let you know if the selection is being done with or without replacement. So let's go ahead and revisit this question with that detail in mind. When selecting 2 marbles at random from the bag with replacement, so we'll take 1 marble out at a time, but when I take the first marble out, I measure its color and I replace it. I put it back into the bag before I draw the second marble out. What is the probability that the first marble is green and the second marble is blue? All right, so we want to know the probability that the first marble is green. And then I like to put the then there just to drive home the point that I'm putting green again, which isn't actually, you might say, oh, that's silly, but that's not a bad question to ask, but that's not the question that is being asked. And then blue. I put then there to make it clear that this is one thing happening first and then another thing happening second. And so we want to consider the probability of picking the green marble first, figure out what that probability is. I'm doing a really bad job of drawing these parentheses. Times the probability of picking the blue marble, given that a green marble was selected first. That's the multiplication rule. So for the first event, you don't really have anything to worry about. You just calculate that probability like normal, right? What's the probability that if I pick a marble out of the bag, that it's a green marble? Well, there's 3 green marbles out of 10 that I could choose. Times, but here we want to consider, well, assuming we got a green marble the first time, what's the chance that when I pick my second marble, it'll be blue? Since this is being done with replacement, that green marble was put back into the bag first. And now when I go to draw my second marble, there's still 10 marbles in the bag, and there's still 3 blue ones in the bag. And so, in fact, the fact that I chose a green one first does not affect the probability of choosing a blue one second because we did this with replacement. It makes the 2 events independent. So actually, I did not have to add that extra, condition to my equation, because if I know they're independent, I can ignore that. I know that the second event's probability is not affected by the first event. So then I multiply these together and I get 9, right? 3 times 3 is 9 over 100, which is 9%. So there's a 9% chance that if I'm going to pick 2 marbles with replacement, that the first marble I choose is green and the second marble I choose is blue, in that order. So again, be careful about what that probability tells you. This is not the probability of picking 2 marbles and getting a green and a blue one. It's specifically getting the green one first and the blue one second. This does not cover the case of choosing a blue one first and a green one second, which again is the same two colored marbles, but in a different order. And here the order matters, right? We're specifically saying green first, blue second. That has a 9% chance of occurring, right? If the selection is made with replacement. But what if it's made without replacement? How does that change things? Right. So now we want to find, it's the same question. What's the probability of choosing the green marble first and then the blue marble second? But now it's without replacement. So when I select that first marble and it's a green marble, I set it to the side. It doesn't go back in the bag. So when I go to make that second selection, there will only be 9 marbles left in the bag, which is going to affect the probability of getting a blue one, since now there's only 9 left to choose from. And so this time we do need to add that extra condition. What's the probability of choosing a green marble first times the probability of choosing the blue marble second, given that a green marble was selected the first time around and was not put back into the bag? Now, the probability of getting a green marble on the first selection is still 3 out of 10. But what's the probability of getting a blue marble now that a green marble has been removed from the bag and was not replaced? Well, there's still 3 blue marbles in the bag, right? We took a green one out, but there's still 3 blue ones left. But now there's only 9 marbles to choose from. So it's 3 out of 9 for us to select a blue marble the second time in this case, which when I multiply these together is going to give me 9 out of 90, which happens to be 10%. Right? So you see it makes a difference. With replacement, there's only a 9% chance of getting green and then blue. But without replacement, it becomes a 10% chance. It's slightly more likely when we do not replace the green marble when we select that one first. So 9 out of 90 reduces to 1 over 10, which is 10%. All right, so these are dependent because of the without replacement. The probability of choosing a blue marble second is impacted by the fact that a green marble was selected first when you make that selection without replacement. All right. So this is the one that blows my mind that I really like to share. And some students kind of react like, they sometimes act like they thought it was, oh, that's obvious. It's definitely not obvious to me. What is the probability when selecting marbles from the bag at random of getting the gold marble last? That it is the last marble that you would choose. So here's how this works. Now, I don't say with or without replacement, but again, the context of the problem makes that clear. In order for me to get to a last marble, I must be selecting these marbles without replacement. Because if I'm replacing them, I never get to a last one. I will always have 10 in the bag every time. So I'm selecting these marbles without replacement. So how do I calculate the probability that if I'm picking out marbles, and I'm going to pick 10 of them, that the gold marble will be the last marble that I pick? So what needs to happen for this is actually a sequence of 10 events happening in just such a way that the gold marble is going to be last. Now, if I want the gold marble to be last, what do I know about the first marble I'm picking? What has to be true about the first marble I choose in order for the gold marble to be the last marble that I pick? And if you're thinking, well, it could be green. Yeah, that's possible. But does it have to be green? No. As long as it's not gold, right? It could be green, red, or blue in order for this sequence of events to be successful, right? The first marble just has to be the one that's not gold. Any other color would be fine. So for the first marble, you don't want to be specific. You don't want to say, well, the first marble has to be green. It doesn't have to be in order for the gold marble to be last. It could be red. It could be blue. It just needs to not be the gold one. So the first marble needs to not be gold in order for this event to occur. That's the first marble. And then the second marble has to not be gold. And then the third marble has to not be gold. And I'm not going to write this that many more times, but that has to happen 9 times, right? So ... over and over and over until you get to the 9th one, not gold. And then you want the last one to be the gold marble. That's the sequence of events that has to happen for the gold marble to be last. So I'm gonna number these, right? This is the first marble we pick, the second marble we pick, the third marble we pick, ... the 9th marble we pick has to be the not gold one, has to be not gold as well. And then the 10th marble, the last marble, would have to be the gold one for this event to occur, right? And because we're using and here, and we're talking about a sequence of events, one happening after the other after the other, this is the multiplication rule. Now, the rule itself really is formulated for just 2 events happening in sequence, but it can be generalized to any number of events. So if you want to know the chance of this happening first, and this happening second, and this happening third, you just multiply those 3 probabilities together. The only condition is that you have to consider the events that came before it. If those events that came before affect that probability, you have to take that into account. But otherwise, you can just string these together. So what I'm going to end up doing here is taking the probability that the first marble, I'm having trouble saying marble now, is not gold, times the probability that the second marble is not gold. I'm just going to multiply these probabilities together. Not gold. Dot, 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 down to the 9th marble not being gold. And then the 10th marble would have to be the gold marble, right? Actually, literally has to be. If the first 9 were all not gold marbles, that last marble you pick is going to have to be the gold one. And we'll see that. We'll see that in the math that we do. Now, I'm not putting the conditional probability in here, but each one of these should have that extra notation of the probability that the second one's not golden, assuming the first one isn't golden, given that the first one wasn't golden. So take into account the events that came before it. This one should say the probability that the third marble is not gold, given that the first 2 marbles were not gold, right? We take into account that these 2 things happened first and then calculate that probability for that third marble. But I'm not writing it out, so we just have to mentally keep that in mind. So what's the probability that the first marble is not gold? Again, you could do the complement. That's the way I've been emphasizing, in this entire lesson. It's 1 minus the probability that the marble is gold. And the probability that the marble is gold is 1 out of 10, right? So we're going to get 1 minus 1 out of 10, or 1 out of 10, 1 minus 1/10, which is going to be 9/10. Right? And which would be the other way you could calculate it. How many marbles are not gold? There's 9 of them, right? 3 green, 3 blue, 3 red. Those are all not golden. So there's 9 marbles that are not gold out of 10 that you could choose from. Now, that's for the first marble. When I go to select the second marble, that first marble was chosen without replacement. So whatever color it happened to be, it wasn't gold, and it was set to the side. It was not put back in the bag. So when I go to select the second marble, how many marbles are left in the bag? We have 9 marbles left in the bag, right? Because we put 1 out. And of those 9 marbles left in the bag, how many of them are not gold? There's 8 left that are not gold, right? We started off with 9 that were not gold, but we took 1 out. So now there's only 8 left in the bag that are not golden out of 9 marbles left altogether. That's for the second marble. For the third marble, right? How many marbles do we have left in the bag? We have now 8 marbles left, right? Because we've removed 2 marbles. We removed this marble here and this one here. So 2 marbles have so far been selected that were not gold and were removed from the bag. So there's 8 left in the bag now. And of those 8 marbles left in the bag, how many of them are not gold? 7 of them, right? Now, hopefully you're starting to see a pattern here. What's going to happen, because we can't keep doing ... So for the next marble, it's going to be 6 out of 7, right? And for the next marble after that, it's going to be 5 out of 6. And for the next marble after that, it'll be 4 out of 5, 3 out of 4, 2 out of 3. And then finally we get down to the 9th marble. For the 9th marble, so we've already picked 8. There's only 2 marbles left in the bag, and only one of them is not the gold marble, right? So that's for the 9th marble. And then for the 10th marble, what's the probability that it's the gold marble? Well, there's only 1 marble left in the bag at this point, and there's only 1 gold marble left. So the probability that's gold is 1 out of 1, which means if you've picked 9 marbles that are not gold, that 10th one has to be, it's certain to be the gold marble, which means the probability is 1 that you will choose the gold marble. Now, what's interesting about these fractions, so that's a lot of multiplication to do, but what's interesting about this, and I'm sorry they're kind of spread out in a weird way, is that a lot of things cancel, right? This 9 on top here cancels with this 9 on the bottom. This 8 cancels out with this 8. So I think this is just kind of a neat thing that happens. All these numbers cancel each other out, and the ones don't really matter, but I'll go ahead and cancel those out. And what am I left with? I'm left with a 1 on top and a 10 on the bottom. And I don't know, this just blows my mind. The probability that the gold marble would be last is 1/10, which is the same probability that the gold marble is chosen first. It's the same either way. And that just doesn't resonate with my intuition very well, because like, think about what has to happen for the gold marble to be last. Everything has to go perfectly through 9 choices for that 10th one to be the gold marble. You have to get not gold, not gold, not gold. So it's just like, it just seems like a sequence of very specific events have to happen for the gold marble to be the last marble, which seems like it'd be harder to do. It seems like it'd be less likely for it to be the last one, because everything before it has to go in such a certain way. But the probability of the gold marble being last is exactly the same as the gold marble being first. It's a 10% chance either way. And I don't know, that shocked me when I found that out, when I did this calculation. And so I like to share that with my students. And I don't know, my intuition would not have told me that the gold marble being last has the same probability as the gold marble being first. But other students say, well, of course, that makes sense to me. So it might just be a matter of, different people might have different intuitions about it. But for me, that was kind of mind-blowing. So, and I just wanted to share that. Now, is that going to be a problem on the test? No, not exactly. But I do want to talk about how you can string these multiplication rules together, right? It can be generalized to multiple sequences of events, not just 2. That is an important thing about this problem that I wanted to address. So now this is another topic I really would like to share with you. I think it's another interesting topic. It's called the birthday paradox. I put that in quotes because it isn't actually a paradox, but it's, again, counterintuitive, like the marble example we just did. And that's why they call it a paradox, because it's not what you would think it would be. So if you had to guess what the answer is, most people are really pretty far off. Our intuition's pretty bad about it. But it actually involves a concept that we haven't really talked about much in this video that gets talked about more in the new section 4.3. And so I think I'm just going to save this for the next video, because this video is already too long anyways. So let's see, I have, oh man, a lot more examples here. A few more. Oh, and I forgot to add some problems for this. Oh no. Okay. So back to the lie detector test results. And now here, and so this is what I thought was going to be there earlier, but now they're telling us there's 98, so we don't have to add it up ourselves. But if 2 of the 98 test subjects are randomly selected with replacement, find the probability that they all had false positive results. So here's a case where we can ask for the sequence to be the same thing twice in a row, right? So for part A, we want to know the probability that the first person had a false positive result, and the second person also has a false positive result. All right. And so we're going to use the multiplication rule, because again, this is a sequence. We're choosing 2 people, right? And we want to know that the first person has this characteristic, and then the second person has this characteristic. So it's a sequence. It's the multiplication rule that we want to use. So we will find the probability that the first person has a false positive result times the probability that the second person has a false positive result. I don't know why I made that into a fraction. False positive result. I think I'm thinking this. Given that the first person had a false positive result. Now this actually isn't going to matter, because this is being done with replacement. So they were very clear about it this time, which means these will be independent events. So basically we're going to choose a person, see if they had a false positive result, write that down, put them back in the pool, and then we'll select a second person. Now, what bothers students about that is, could we pick the same person twice in a row? Yes. With replacement, that is possible. You might choose the same person again. And that's just the nature of the situation. But it doesn't mean the math is bad or anything. So you might pick the same person twice in a row, but they're being replaced. So we select a person, get their information, put them back in the selection pool, and then we select a second person. And it's rare, 1 in 98 chance, right? But we might accidentally shouldn't say accidentally, but we might select the same person twice, right? But that's a risk we're going to live with. And because with replacement, the math is usually easier anyways. You'll see why, right? So for false positives, how many people had a false positive result? Right here, right? False positives are right here. 15 people out of the 98, right? So there's a 15 and 98 chance of selecting a person with a false positive result when I go to select that first person. And because they are being replaced, they're being put back into the selection pool. When I go to select the second person, all the numbers are restored. We're back to 15 people with false positive results. We're back to 98 people altogether to choose from. So what's nice about the with replacement is that if you're looking at the same characteristic twice in a row, like we are here, the probability will be the same twice in a row. And what's nice about having the probability just stay the same in both cases is since you're multiplying the same number to itself twice, you can just use exponents. Now you might think it's a little silly with 2, and it kind of is, right? Is it easier to do 15 over 98 times 15 over 98? Or is it easier to do 15 over 98 to the second power in your calculator? It's probably about the same amount of work either way. But what if we were going to select 5 people? And we want to know the probability that all 5 of them have a false positive result. If I'm doing it without replacement, the numbers are going to keep changing every time, like the marble example, right? The first one would be 15 over 98. The second one's going to be 14 over 97. The third one's going to be 13 over 96, right? And it's going to keep changing each time. And then you have 5 different fractions that you have to multiply together. That's going to be a pretty cumbersome calculation. Whereas if you do this with replacement, it's 15 over 98 all 5 times. So then all you have to do is 15 over 98 to the 5th power. It's much easier to type into your calculator when you have that many. And so that's why with replacement, even though you're taking the risk of selecting the same person twice in a row or twice in the 5 times or whatever, it just makes the math easier. And the answers are not that different from each other. You'll see, because for part B, we're going to do without replacement. You'll see as a decimal, you really kind of get the same. They're pretty close to each other. They're not exactly the same, but they're close. So let me get my calculator out. I'm sorry, we're already at 1.5 hours on this video. That's too long for a video. I don't know what else to do though. I guess I could chunk it up into separate videos, but it's got to get covered one way or the other. So I'm just going to leave it up to you to chunk it up. So watch as much as you can, pause it when you've had enough, work on some of the homework if you want, whatever, come back to it when you're ready for more. So 15 over 98 to the 2nd power. On the phone, it's kind of hard to do exponents here, 2nd power. Okay. So we get to 3 significant digits, right? Because that's the rule of thumb. 0.0, that's not a significant digit, but this one is 2, 3, 4. So about 2% chance of that happening. All right. Now, same question. What's the probability of choosing 2 people in a row that have false positive results, but this time without replacement? That way we don't select the same person twice, right? That'd be the benefit of doing it without replacement. So we want probability that the first person's false positive and the second person is false positive. And so we're going to use the multiplication rule. Probability that the first person's false positive times the probability that the second person is false positive, given that the first person was false positive. Now for the first calculation, for the first probability, it's going to be the same. Let's start with the other number. There's 98 people to choose from altogether, and 15 of them have a false positive result. So the probability is going to be 15 over 98. But for the second person, we have to take this into account. And this time it matters because it's without replacement. So as I already mentioned, there's one less person to choose from now. We've already chosen a person, and now we've sent them home, right? So think of it that way, right? We make a selection, we pick a person, we write down their outcome, and then we send them home. We're like, okay, you're done for today. You can go ahead and go home. How many people do we have left to choose from? We have only 97 people now, right? Because we sent one home. And of those 97 people, how many of them still have a false positive result? Only 14 now, because we sent one of the 15 home, right? Originally, we had 15 with a false positive result. We sent one of them home. So now there's only 14 left, right? And so that would be the probability that the second person would have a false positive result, considering that one person with a false positive result was already sent home, all right? Now we have to multiply these together, but now we can't use exponents, right? We have to, so this is the drawback of without replacement, is that it's going to lead to the situation where every fraction is going to be different, and the calculation can become more challenging. Right? So 15 over 98 times, I probably should use parentheses here, So it'd be much easier to do if I had a calculator with me. I still have not been to my office in like 3 months because of the coronavirus stuff. And I didn't come home with a calculator. I think my kids might have one, but I'm just making do with this iPhone calculator. It gets the job done. So this is going to be 0.0221. So you see, it's still roughly 2% chance, right? 2% chance, 2.21% versus 2.34%. It's very close. But the math is easier to calculate if you do it with replacement versus without replacement. And since it gets you pretty close to the right answer anyways, it's very common. I'm not saying you're allowed to do this. On the homework, if it says without replacement, you better do the calculation without replacement, unless it says you can use this rule of thumb, which I don't know if you saw it here, but I said, I don't have an example of this, but this 5% guideline for cumbersome calculations, if it says, please use this guideline, then even if it is without replacement, you can do the calculation as if it's with replacement because you're going to get an answer that's close enough, right? But there is a limit to how well this works, and so you have to follow this 5% rule. If a sample size is no more than 5% of the size of the population, treat the selections as being independent, even if the selections are made without replacement, so they are technically dependent. So even if they are being done without replacement, you can treat the selections as if they were with replacement so that the probabilities are independent, so the fractions don't change. But only if your sample size, only if the number you're selecting is no more than 5% of the population size. So for the example I gave, actually I kind of broke that rule because I said, well, if you're going to pick 5 people, you might want to treat it as with replacement, but 5 is probably, it's a little more than 5% of 98. And so I wouldn't be able to do that for 5 people given this guideline. 5 is too many. It starts to diverge. The answers become too different from each other at that point. So, but for 4, that's less than 5% of 98. And in that case, even if my selection's done without replacement, I can do the calculation as if it was with replacement to keep the calculation easier to do. And the answers will be roughly the same either way. Okay. And I would like to do an example of that, but maybe I'm just going to leave it. I feel like this video is pretty long already. And so maybe I'll just leave it at that. If 3 of the 98 test subjects are randomly selected without replacement, find the probability that they all had negative test results. Is it unusual to select 3 subjects without replacement and to have all 3 of them be negative test results? So really kind of the same question as we were just doing. Let's go ahead and use the 5% rule on this. And if on the homework you're not sure, am I allowed to take this shortcut? View an example and see what they do on the example. And if they use the shortcut on the example, then you're more than welcome to it as well. If they don't, then you probably should do it, the right way without replacement. But I'm going to go ahead and use the 5% rule because, 3, that's going to be, 3 different fractions. I'd rather them all be the same. All right, so I'm going to use the 5% rule for cumbersome calculations. And so I'm going to find the probability of having 1 negative test result for the first person, and the second person having a negative test result, and the third person having a negative test result. And I'm going to treat those selections as if they were with replacement in order for the probabilities to be independent so that the calculation will be easier to do. All right, so negative times the probability that the second person has a negative result times the probability that the third person has a negative result. All right, now let's go back to that chart. Whoops, hit the wrong button. So negative, remember, is this entire row right here. And there are 41 people that had a negative test result. And so the probability of selecting a person with a negative test result would be 41 out of 98. If I was doing this with replacement and being literal about that, then for the second person, it would be 40 out of 97, right? There would be 1 less person to choose from, 1 less person with a negative test result. And for the third person, it would be 39 out of 96, right? 2 less people with negative results and 2 less people to choose from because 2 people were already selected by the time I get to that third person. So this would be the proper calculation to do. But you can see that I'm going to have to type in these 3 different fractions. So I am using the 5% rule, and the 5% rule says just go ahead and treat it as if it were with replacement. So this will be 41 over 98. I'm going to replace that person, so I'm back to 41 negative test results out of 98 people. And then I will replace that person, so I'm back to 41 negative test results out of 98 people. So with replacement, that probability just stays the same all the way through, because with replacement, they're now all independent. The probabilities won't change as we go through these events. And since they're all the same, I can use an exponent. This will be 41, I almost put 48, out of 98 to the 3rd power. And that's just going to be a little bit easier as a calculation for me to do. All right, so let's go ahead and type that in. So we have 41 over 98. And then I'm going to raise that. Okay, come on, phone. Raise that to the 3rd power. Okay. And so I get 0.0732. So I know it's been a long video, but I would encourage you as an exercise, find out what this is equal to, and then compare the answers. And you should see they're fairly close together, right? But go ahead and do the calculation the proper way just to see what kind of difference it makes. Now the question, the last part of this question was, is this unusual? Is it rare? So remember, I know it sounds like it's asking your opinion. Is it unusual? But it's not. It wants you to use a rigorous rule for making that determination. And remember, we said the rule was less than 5%. It's unusual if it's less than 5%, or equal to 5%, I guess. This is slightly more. So we're going to say, no, that's not unusual, right? This is greater than 5%. It's about 7%. And so this is not unusual, even though it's close. We want to be consistent. So we don't want to have like arbitrary where sometimes we say it is and sometimes we say it's not, depending on our gut instinct. We have a rigid rule to follow for making that determination, right? If it's less than 5%, it is unusual. If it's more than 5%, it's not unusual. All right. Okay, so one last example here. A quick quiz consists of a true-false question followed by a multiple choice question with 4 possible answers and only one of them being correct. An unprepared student makes random guesses for both answers. So they're not ready for this quiz. They guess on the true-false. They guess on the multiple choice. Right. Consider the event being correct with the first guess and the event of being correct with the second guess. So consider, it's not asking for a probability here. It's just saying, think of these 2 events, being right on the first answer, being right on the second answer from guessing. Are they independent of each other? And if you're just randomly guessing, the answer is yes, they are independent. Whether or not you get the second question right is not affected by whether you got the first question right, because you are just guessing on that first question. You don't know what the answer is on that, and you're just guessing on the second question. So it wouldn't be a guess, like it wouldn't be a random guess on the second question if you took into account your answer on the first question, right? And so for it to be truly random, you're not thinking about that first question when you're answering that second question. And so therefore, it would be independent. For you to guess the right answer on that second question is not affected by if you got the right answer on the first question or not, because you're just randomly guessing and you're not taking that first question into account. Right? So yes, these are independent events if we are making random guesses, which is what the problem says we're doing. What is the probability that both answers are correct? Right? So we want to look at the probability that we get the right answer on the first question and then get the right answer on the second question. I'm sorry, I don't know if you guys can hear my computer starting to make some noise. I guess I'm probably going too long on this recording and it's starting to complain about it. So I hope it's not too audible in the recording, but if it is, I apologize. So we'll use the multiplication rule because, again, this is a sequence, getting the first one right and then getting the second one right. And so we'll multiply. And because these are independent, I don't have to have that extra condition of assuming that the first one was right. I don't have to say, what's the probability that the second question is guessed correctly, assuming the first one was guessed correctly, because it doesn't matter. It's independent. The probability is not going to change because of that. And so what's the probability of guessing the right answer on the first question? Well, it's true or false. How many answers do I have to choose from? 2. How many of them are correct? 1. So there's only one way to get the right answer out of the 2 answers that I could choose. For the second question, it's different, right? How many answers are there to choose from? There's 4. How many of them are correct? 1. And then I multiply those together and I get 1 out of 8. So you have a 1 in 8 chance of getting 100% on this quiz if you randomly guess, which is about 12.5%. So is that unusual? Would it be unusual for a person to just randomly guess and get 100% on this quiz? No, 12.5% is not unusual. 1 out of every 8 students who do this are going to get 100% on this quiz, right? Now, does that mean you shouldn't have to worry about studying and you should take this strategy? No, because while that's not unusual, it's still pretty bad odds. Only 1 out of every 8 of you that do this are going to have it work out in your favor. 1 out of 8 of you, or not even 1 out of 8 of you, 3 out of 8 will get zeros on the test, and half of you will get 50%, right? And so it's bad odds, right? And so even though it's not unusual, it's not a risk that you want to take on this quiz. So that will be the end of the video on the now lengthy section 4.2, which maybe I'm spending too much time on anyways, but I hope you found it useful and interesting. And I will see you in the next video, which will either be 4.3 if I decide to go ahead and cover that, or 5.1 if we go ahead and move on to chapter 5. Thank you for watching.